Good morning, everyone. So today we are going to talk about how we actually build a compute pipeline for contact insights, and I'm going to talk about our journey all the way. So let's introduce ourselves. So I'm Praveen. So we're part of. I work at Salesforce. I kind of run a couple of data teams there, trying to ingest a lot of our customers' data, trying to process them, trying to build some insights of it.
Hi, I'm Jidong. I'm also working for Salesforce in same team as Praveen, and I'm technical lead in data pipeline and some software design.
Sounds good. Hope all of you are having a great morning. And this is one of my best times to present, because in my previous conference, I was giving a talk in the afternoon after having wonderful lunch, and it was so hard for me to keep up. So this is definitely the best way, because we have a coffee, we have a breakfast, we have the right keynote. So let's jump into that. So we have limited time and unlimited agenda. But we'll try to kind of like walk through the agenda before we can step in each and every steps. So we're going to start with the high level of introduction. So we're going to start at 40,000 feet height. So what we're going to, what our organization does and what kind of products that we build. And then we're going to go into maybe 20,000 feet, trying to talk about the context of what is important for us trying to build a product. And then we go into 5,000 feet of talking about how we're trying to design the product. And then in the last one, in the key problems solved and lessons learned, probably we're going to dig a tunnel and go into underground and trying to see what we're going to build. So I'm going to talk about, so eventually we're going to cover all our journey that we end up taking, because like from the time we begin the project all the way from the time to the time where we have the project. So there's a lot of ups and downs. Like we learned a lot. There's a lot of problems that we end up facing. So as part of the key problem solved and lessons learned, we're going to talk more about it. My whole point for the entire journey is that I'm trying to avoid saying that once we're under the tunnel in the underground, I don't want to look up saying that, oh boy, we did a mistake. And I was trying to avoid it for the whole journey. But let's go into that. So there's a forward-looking statement. So Salesforce is a public company, and we're going to talk a bit about future development projects as well. So all the purchases of Salesforce products should be from the commercially available products instead of my presentation. So before we jump into the actual discussion, I always want to ask a question. So today, just want to kind of have an analogy with this presentation. How many of you guys use Spotify, and how many of you actually use Discover Weekly? Do someone hate it? That's a good number. So as you try to, get you right, so probably you're thinking, why I'm talking about Spotify? But I'm not promoting to use Spotify, but I'll be trying to make an analogy of how a product could be similar to the consumer products that you use every single day. So this is the 40,000 feet level. So Salesforce is a customer success platform, which actually has a huge spectrum of customers, users, activities across marketing, sales, services, and it has all those IoT capabilities and analytics capabilities. And we use all this data trying to kind of like empower, we use all this customer data and then try to embark all this AI and the data science pipelines, trying to empower our customer insights to build some smarter apps and smarter products for the customers. And today we're going to talk about a specific cloud within Salesforce called Sales Cloud. And it is one of the most popular used product within Salesforce. And within Salesforce, we're going to step in a bit further down. So our teams is essentially building some pipelines for ingesting a lot of our customer activities, mostly in terms of their emails, meetings, contacts, their interactions with the users, their calls, their tasks, and a bunch of different stuff that we capture from all the users. And here we just presented only a couple of instances just to have a context for us. And once we capture all those emails here, we actually kind of like extract some insights using some of the classifications. And using those classifications, we actually show those insights in our apps. Like we have some inbox app, which is an email, which actually shows up some insights about each and every email and each and every contact. And then based on these insights, we suggest some actions to our customers. And similarly, using the contacts, once we kind of like ingest all the contacts, we actually build something called a graph kind of a thing. We'll talk more about it further. And using all those contacts and all those emails, we use them together, trying to kind of like gather some helpful insights for our customers. And then we try to build some products and services. And of course, using all those contacts, it doesn't mean that the Salesforce Tower is not part of it, but it is one of the proud things that we always keep showcasing. But using all those contacts from the contacts and from the emails, we actually eventually try to empower a lot of insights in our AI inbox and our timelines. And we try to let our users to stay on top of what they want to. So it's very important for us trying to kind of bring some relevance to all our applications. And here is the exact app that we're going to talk about, like how we build a pipeline to generate the insights for the specific app. As the saying goes, right, so it's not what you know, but it's who you know. So here's the exact thing that we're trying to solve here as well. For any sales rep who wants to make a deal or who wants to sell their products, their services to a different new organization, the first hurdle for them is the connections. How do we need to get to know about people in a new organization? And it's always harder for them trying to kind of keep asking around people, keep trying to ask around different their users to help them trying to make an introduction. But if there is some other people in the common friends who can help them trying to introduce easy quicker, right? It just helps them trying to accelerate the process. So here's exactly what we're trying to do. So for anyone who wants to make a deal, for anyone who wants to make a contact, so we actually know that here is all the previous conversations you're having in your emails, in your meetings, in the past history, in the 6 months to 1 year or to a number of years. And we know that with all the meetings, so there are some common contacts who you can leverage trying to make a connection and trying to talk to them who can introduce you to this new contact, to this new influential person who can help you to close the deal faster. So that actually helps us here. So initially, we show up with all these closest connections, who they are, and why is it closest connection, and how strong is the closest connection. And we actually describe how we actually evaluated why this is a stronger connection as well. And so that actually is a kind of more the introduction of what we try to build. And now we are going to talk about what is the context of how we thought about it. So most of you people has been using these products in almost every single day. But I'm going to quickly go with it, right? So Apple, Amazon, or Facebook. So it's all about so it's every time whenever we try to do with the user interaction with any of these apps, it actually captures all this information with us, and then using all those contexts that we give it to those apps, it actually helps us trying to deepen the context. So there's a kicker thing, right? So here's a kicker, right? We strongly believe that the data plus algorithms plus compute can always give us a killer apps. And all these apps actually use the same kind of concept, trying to give us a killer kind of functionality for us. But the common thing across all these apps is only one thing. It's called user context. But there's a difference of what these apps provide from what we provide. So Salesforce being an enterprise app, so it's very hard for it trying to kind of use the same user context being used in the consumer apps versus the enterprise apps. So in the enterprise apps, things are very different. For us, there are a huge number of things like the data privacy, data retention, security, and the boundaries of the data, and the user consent, and the customer consent. So we need to consider all those important factors for us trying to conclude how we can build and what kind of user context that we can use before going forward. And of course, the context has to be scoped. Sometimes it has to be at the user level, and sometimes it has to be at the team level, and sometimes it has to be at the org level. So we need to actually kind of make sure we have a strong boundaries so that we cannot share one org's information with other. Like for example, if Citibank is our customer, we don't want to share the Citibank information with Bank of America. So it's very important for us trying to build some models, build some context for an org scope boundaries itself. And of course, this data is actually very rich because so it's not only to specific contacts we're going to talk about, because whenever someone is having conversation across multiple groups, so they could be talking about some contacts, they could be talking about some products and services and companies. There's a lot of information we can always gather from all these conversations. But for this presentation, we're going to scope it to only context at this time. And the other point is that it's very dynamic. As there's a lot of millions and millions of activities happening with a specific organization, so it's very hard to catch up. So we need to kind of constantly augment our data and context to keep it updated. As one more point is that, so the orgs that I'm talking about, it could be as small as only five people in an organization, or it could be 100K users in the organization as well. But Salesforce has to actually kind of address all these different sizes of the organizations to make it a consistent experience for them. And here's a bit more information of why. So we spoke about the user context, and we spoke about the enterprise context as well. Now, how to use this context to deliver these deeper insights. So as we mentioned, right, so we speak about a lot of different emails and conversations that our customers are having with their users. But it's not a simple classification that we're going to build now. So with each and every email and conversation they're having, yes, we can have some kind of stateless insights to them. But would that give us a context? Not really. It can turn up into a simple classification model itself. What we really need is a strong, deeper context of the users so that we know exactly what they discussed in the past, and then we can keep on building on top of it. So, and for example, here is this email discussing products and services that my company sell. So if you know that the history, what kind of products the company actually always sold, it actually helps us trying to prioritize that specific conversation to say whether this is an important conversation or not. And similarly, there's a lot of things are they discussing about competitors. If someone is trying to talk about competitors, we know that you need to actually make it as a priority because they're going to they're going to reach to a different competitors itself. So it's very important for us trying to see what they're talking about, and it's very important for us to see what they actually already discussed in the past. And eventually, this context can help us try and deliver some deeper insights. And now we know that what kind of context that we need to build. So now we're going to talk about a bit more how we thought or what do we think and how we design to use this context or trying to represent this context into an object model itself. And one of the common things that comes to our mind naturally is that since we're talking about some contacts, some relationships, how stronger it is. So one of the common approaches is that probably graph is one simple approach that we can start with. And graph can help us try and kind of build the entire representation of all the activities and conversation into one specific diagram. For example, there's a lot of emails and interactions are happening with multiple customers and their users as well. And you can see in this diagram, right? So if, like, for example, all these hollow nodes represents the users in the org, and all these the colored ones represent the customers. Now we know that which sales reps are talking to which customers. And if there's a new node that actually comes in, and if they want to talk to Mark, and then they know that quickly that, oh, Joe is a guy who can help them trying to introduce to Mark immediately. And as I mentioned, these orgs could be having a lot of thousands and thousands of contacts, and then it can always start with a small number of contacts, and it can always go up to a huge number of contacts itself. And these contacts keep on changing every time. And perhaps more important is that those contacts extend beyond the org. It's not only within the org. Those contacts actually go beyond the orgs and the customers as well. And these orgs are having millions and millions of events per week. So that actually helps us. It actually enforces trying to keep on augmenting this graph with actually adding a lot of information, a lot of nodes, and making sure that to consider all these important meetings, because there could be a lot of like spam meetings or spam emails and phone calls. We need to actually always classify how important is a meeting and how important is an email. And based on all those activities, we need to augment the graph accordingly. And now, since we have the graph built, so how can we use this existing representation of graph, and how can we add those contexts to generate some closest connections? So what we call is called Conditional Services. So we have a graph here, and with all these graphs, we are trying to kind of generate who is a particular email from, and why should I care, and what is the role, what's the latest communication, what's the meeting history, and what's the mutual friends, what is the contact info. There's a lot of information we can always gather from each and every conversation. And we use all these conversations as a context, and we build some models on top of it. Using those models and using those contexts and using the graph, we actually try to derive some insights from it. And those insights is not just the mutual connections itself. It can actually go further beyond. For example, if I have to talk to reach a new organization, who can help me trying to reach a new person in this organization? Or who is the influence in this organization? And who can close the deal faster? Who is the executive? And who is the last person who actually closed the deal faster itself? So there's a lot of information that we can actually derive. Like, for example, the best time to email to a specific person itself. There's a lot of properties that we can add to each and every node of this graph, which can help us trying to derive some insights. So now we know that we have a graph, and we can use some context to derive some insights. Now, actually, let's actually jump into the the graph itself. Like, what is the architecture that we use trying to like build all these insights? So here's a high level the graph generation architecture. So as I mentioned earlier, so we have a lot of stream of activities coming from our customers, and we use Kafka. So Kafka is our integral piece of our software. And then we use like all Apache Spark compute pipelines, trying to kind of like aggregate and batch all those incoming near real-time data into a small, short windows of times. And then we build something called activity store, which is kind of a data lake, so that all the information of all the users can be stored and aggregated into one specific data lake itself. And we can potentially use this data lake to bootstrap and trying to kind of generate some graph services. So the graph services here is more about trying to take a representation of existing the flat data into kind of more an object model, which actually helps us trying to understand, for example, for a specific organization, here is the exact representation. I know this is the National Alert Day, so I would expect all these phones will go with alarms. So for each and every organization, we should maintain a different graph so that it doesn't actually overlap with a different organization itself. And once we have a graph, what should we do with that? Of course, number one is that we should persist in case of failures, because we don't want to lose the graph. And at the same time, whenever we want to increment and augment the graph, we always have this build graph so that we can use this graph and try to kind of augment on top of it. And once we have these insights, and how do we surface those insights to our customers in the apps? So we actually kind of like, you have an index store in terms of our Elasticsearch. We index all these insights from the graph and try to put in an index store. And we have an API layer which actually helps us trying to quickly query all those closest connection or some other kind of queries, and helps us trying to surface all those insights to our clients. So this is the high-level diagram, and let's try to kind of dig in what is exactly we have in the graph. So in the graph, like, we have something called once we have a delta badge, we try to use so using the library that we get from our data science team, we build some data, some RDDs of all the activities. And so as you can see in the graph, right, so we have the nodes and we have the edges, right? And with all those nodes, each and every node can represent a person or a company or a product. It could be any part of it. And it actually kind of varies based on the need that we have. And once we have all those participants in the nodes, and we have all these connections and edges between them, and the edges represent how strong the communication is between them and how strong is the relationship between them. And once we have all these participants and events, we try to consolidate both of those vertex and edges, and trying to kind of merge those vertex and edges to make some RDDs and update the raw graph itself. And that actually helps us trying to build a new graph from bootstrap. But what happens if we already have a graph, and how can we try to kind of use this incremental graph, trying to make sure that we don't need to regenerate the entire graph every single time? And of course, every time whenever we try to build a graph, we just want to persist it so that we don't want to lose a graph. And since we already know about like what we have in the graph, and here's our Spark pipeline that actually kind of outlines what we do in general in our Spark jobs to build this graph. As we might understand, right, because we don't have only single org or single user, we have thousands and thousands of orgs, and with each org can contain like a lot of users, from all the way from 5 to 50,000 or 100K or users as well. And so which means that we need to use our limited Spark cluster, trying to kind of like parallelize as much as we can, and trying to kind of like run multiple jobs in parallel and trying to complete those connections. And of course, Zirong is going to walk through exactly how we come with the parallelization and what kind of bottlenecks that we hit. But here is a kind of high-level diagram is that. So our Asgaban, which is our job scheduler, tries to talk to a record store, which actually contains all the orgs information. And based on all the orgs, it actually kind of categorizes and classify that these orgs belongs to small category, medium category, all the t-shirt size like M, small, and XL and double XL. And based on that, we actually kind of like customize our Spark job, like gives us more memory and resources, and helps us trying to kind of like execute all those things in parallel. And it actually kind of outlines that for each and every job, there are multiple executors trying to kind of load data from our S3 and trying to kind of like compute the graph and trying to index them and trying to show it. So this actually kind of outlines that we have multiple jobs happening in parallel, but someone can ask us that for a single organization, why would we be having 2 jobs? So we have like multiple stages here is that, so in the first stage, we load all the activity data, and we create the graph, and then we checkpoint the graph, and we load into the file store. But once we have the graph in place, we need to have a different job. So the first job is actually more about memory intensive because, it's more about the resource intensive. We need to have more number of cores to load a lot of data from our file store into the Spark jobs itself. But the second job is all about the computing the insights, which actually requires more of memory than resources in order to compute the insights. But anyway, we're going to talk about all these advantages in the next slides. So that actually kind of concludes the architecture diagram. I'd like to call Zedong, trying to kind of talk about the problems and lessons that we learned as part of our journey.
Thank you, Pavin. So let's get started with our long journey of some technical stuff. I got this project from my manager a couple of months ago, and I initially thought because it's quite straightforward, because we have the library which was generated from our machine learning team. We have our own Spark cluster. We have our data pipeline, and I thought it just needs to integrate everything, and it's run in our Spark job. But obviously, it's not that case. So we first have some memory issues because, as Praveen mentioned, we have a lot of organizations, thousands of organizations. But every organization can have different number of users. It can as small as 5 users or 1 user, but it can as big as thousands or few hundred thousands users. And when we start with the project, we start with some brute force way, just applied some medium memory executors to every organization. And we found it definitely shows these out of memory issues, exceptions. When we run into bigger org, then I report this and say, okay, let's do the simple way, just increase the memory by 2x. Yeah, it kind of resolves a lot of issues, but we will see some further issue. It's over provision. After a couple of days, we get like a cost bill from our infra team. Hey, you use too much memory, and we found, yeah, for some small organizations, we definitely use over capacity. So. But then we start thinking, how can we apply the configuration of each Spark job for every organization? Because every organization has its own size in terms of users' activities. So we think probably we can do some grouping. We can group by users, number of users. We assume the organization with a similar size of users, they can have a similar Spark configurations. So we come up with a strategy called a bucketing strategy, which we, for example, we create 4 buckets called small, medium, large, and extra large. And for small bucket, it has the number of users which has less than 10. Medium is 10 to 50 plus, and the large bucket probably from 100 to 200. Extra large is more than 200 users. Then we can pick up with some organizations, and we tune the memory, increase the memory, decrease memory, and we look into the JVM. We found what is the optimal memory for this each bucket within organizations. We found, and we tune the number of executors. We write the graph, we run some analytic tool to compare the number of executors per bucket and see how the performance gain when we increase the number of executors, which help us to not avoid the memory issue, avoid over provision, resource issue. Also, the last thing is we also want to tune the partitions. As you guys know, the Spark, when writing or reading, it always comes with RDD and in partitions. So partition is a key when you write into the files. So we want to make sure the partition is reasonable designed for every bucket. Then we just, and I just kick off the job and I just go home. I saw the job will complete when I reach home, but obviously it's not that case. When I reach home, I look into Spark UI and I found the job just got stuck and it could not even just read the data. It could not even start reading the data. The progress just shows 0. Then I start adding the logs everywhere and then dig into the source code, and I found this is one line where the job got stuck. We use Avro format as our graph output, and we just use this simple line and one line to read the data. It's the library, the Spark Avro library is too smart that it try to collect. When you call this one line, it's just too smart that it collect all the keys associated with the values, and doing the metadata fetching across the wire to our service provider key value storage to find the total size input, because Spark assumes you will read a very big chunk, and it try to get the metadata so it can smartly partition those big chunks into partitions and distribute them into executors. But in our case, as Praveen mentioned, we have our micro-batching streaming jobs as our upstream. Every few minutes, we will aggregate the files per organization into our data lake, which cause some issue that for very big org is definitely good because they have a huge amount of traffic. But for some small orgs, like 1 or 2 users, within few minutes, we won't expect too many traffic. We may just get like 1 email, 1 meetings at 15 minutes. So it introduces a lot of small files. It's like 1 kilobyte, few kilobytes, which kind of kill us. So for some hacking or some short-term solution, we say, okay, I know the size of each file is too small. It's just very small. And I know how many files I want to read. I will do the listing and provide the key. I provide all Avro files at one time. So instead of calling this Spark native library, I will start doing from scratch using the native support parallelized API, which I provide all keys, and I read and I distribute those keys into executors, and let executor to read the data in parallel. Instead, let just Spark driver as a single thread, which will read the data in very slow mode to get the metadata. So with this approach, we are able to load the data faster because we're doing a lot of parallelizations. But as you guys know, when we're building a big data pipeline, the small files is always the headache. It's not the best practice. We always want to avoid those small files to build the less number of files, but with bigger chunk, like 1 gig, 2 gig data. So I wrote some scripts and try to compact those 15 minutes files into 1 day data. If it's 15 minutes, which means every day we may produce 96 files. If it's a big file, we are fine, but it's too small. So we reduce the number of files into 1 day, which means cut down the number of files from 96 to 1 file per day for some small and medium organizations. And we found there's a huge performance jump. I still remember because we did this research and write some simple scripts to our performance environment. And also our performance team also doing the regularly performance tests again less. Then one day, one guy come to my desk, oh, I saw my performance gain by 3x. I didn't change any code. What magic are you guys doing? I told him it's because we run some compaction. But we can compact this at one time, but as the file keep accumulating, we want to have some smart way or some framework or it's a scheduler. It can automatically run every day instead of we as a developer manually kick off the script every day. So we built our compaction job called Compaction Framework. So every day we schedule this data compaction job and read and figure out what is the organization like based on the size of which need to be compact. And we run this job, aggregate them by organization, and we write into one day's data. So that approach helps us improve a lot of the performance in terms of reading part. Now I thought, okay, we just apply the one Spark jobs per bucket, and we know the number of the configuration per Spark job. It's time to scale up. So we start with a 100 organization in running one Spark job per bucket, and we let it run. But it takes extremely slow because and we increase the number of executors, increase memories. It helps a little bit, but not in scale way. So we thought, okay, we can scale up the memory, we can scale up the number of executors. Why don't we scale up the clusters, Spark clusters? So in this architecture, we first partitioned the organizations, grouping them by size into buckets. Then within one bucket, instead of creating one Spark job, we create multiple Spark jobs. And each Spark job will read for a set of pre-assigned jobs, pre-assigned graph generation jobs, and it can run in parallel. So for example, a small bucket, we get at least, let's say, 900 organization graph generation jobs, and we have 3 partitions. Each partition has one Spark job, which means every partition may have 300 Spark jobs, graph generation jobs running. So as far as so on, so we can scale up by scaling up the Spark clusters. And then I just say, okay, we almost done. We can scale up that, but we still see some like a very common case, very common issues that we found a lot of Spark jobs just complete super fast, and maybe a few days. But it's some Spark job, like in this case, like job 3 and job 8, they are running more than 3 days, and other jobs just running for 1 day and it's complete, which we found is kind of unbalanced issue. It's a hotspot issue. Again, our team did some research, and we dig into the job itself, and we found, because we make an assumption that every user may have similar activities, but it's not the case. Even we have two organizations has the same amount of users, but users' activity varies a lot. One user can send thousands of emails a day if he is super active. One user may just send 1 or 2 emails a day, which causes the hotspot issue. And how can we resolve the issue? We have a discussion, and we found that because we pre-assigned, it's due to we pre-assigned the users into bucket and partitions. Why don't we let the workers spin up a pool from the queue? So instead of we pre-assigned as a previous bucket graph shows, we introduce our simple queue as a Kafka queue. And for when we're doing bucket strategy, we are doing similar group by number of users. And for each topic, like topic 1, it will assign all the graph generation jobs requests into this topic only. And for this topic, we will have multiple workers which will read from this topic, and they read it in the blocking way. Wherever topic has some request, any idle or any freed workers will try to pull from this topic. So we make sure none of these worker is idle, is not doing anything. It all as long as the topic is not empty. So in this case, we avoid the hotspot issue, and I thought, okay, and we are able to scale up this generated all graphs for all organizations at first time ever. Then our team was just celebrating, and we bring this news to our manager, and we maybe expecting some rewards. But as you know, the manager always asks more. So we have some useful tips before we go to the next half of the journeys. If we have like a variance data input, we can have like bucket strategy, which we can group these similar size of users into buckets. And if we want to scale up, if we have a huge amount of graph generation jobs in one bucket, we can again partition those jobs within one bucket. So we can scale up by increasing the number of Spark clusters. And the tiny file is always the headache for us. If we can avoid that, definitely avoid them. But if we can't, we can avoid suffering from these tiny files again and again. We can have some compaction job, which compact them, even it has to read from tiny file and doing aggregation. But the next time, all our downstream will be super happy with these compaction things, compaction big files. And if we see the hotspot issues doing the downstream jobs, we can try to balance those load across multiple workers. If we can use one single queue, let every with a pool, and let the downstream worker to pull from this queue, it can definitely help. So as I mentioned, our manager always asks more, and what is it? Because this first time we ever generate a full graph for every organization, we were super happy, but manager saying, okay, what about the incremental one? Every day, how can you generate the new updates for you, new activities? So, okay, I may cancel my vacation and rethink about how can we do that. So there's some obvious way that, okay, let's just write again across all organizations, read all activities up to date, then regenerate the graph. Or we can do it more smart way, that we dump this existing graph somewhere, and we will read only the delta from last checkpointing, and add those activity at this node edges into existing graph, which is called incremental updates. So as the graph shows, we have the first day, the day 0 job called onboarding job, and it loads everything and generate a graph. And we have built one data lake called the graph data lake. And this data lake will store all the graphs in our, we store all graphs for every organizations. And every day, we just need to increase around the regular jobs and read the data, the delta, we call it delta data, from our activity data lake, and combine this and produce the new graph. This is a quite smart way that we reduce a lot of time instead of reading from scratch. But the failures can happen. When I read this, when we run these incremental jobs, we found because we introduced some complexity of this, so we have to add with complexity and introduce more IOs, and we found that a lot of Spark jobs succeed, but few of them failed. And I tried to search the logs, and each Spark job has hundreds of stages. Extremely hard for us to find which job failed and which job succeed, and due to why. So, and if a job failed, how can we recover it? How can we check each state of each jobs? Which bring in some new design we proposed is a metadata store. So these are the existing graph. So we introduce the metadata storage, and every time when the activity like completed onboarding, it will checkpointing with the metadata database. Incremental jobs will read the checkpointing from the metadata database, and if any of the incremental job failed, we will mark as a flag. And at the end, we will have a retry job, which will read from the database and find what specific job failed, and rerun it again. If it still failed, we have some alert and dashboard for this. Now we have to talk about how can we generate a graph. But we want to build insights on top of graph and let the customer and APIs to read this data. So we use our indexing store, use Elasticsearch. But Elasticsearch, as you guys know, the indexing corruption is very common things. How can we avoid this? Especially during the indexing updates. So here is the diagram. Like for day 0 jobs, it run graph and generate the indexing, and it push to our API server. But for the incremental jobs, again, it run the same flow, but it read only incremental activities. But it doesn't write into the new existing indexing. Instead, it write into the old index, completely new indexing, and it run the validation jobs, which will see, okay, is the job indexing complete? Am I missing any data? If it succeeds, it will cut the while of the old indexing and swap into the new indexing, so customer can see the freshness of the data. But what if the job failed, validation job failed? The job will automatically correct the indexing from the old indexing. For example, if the job has some missing data or has some corrupted data, we automatically copy them, correct them, and push into the new indexing. Then run validation job again. And as long as it can pass the validation, we will do a swap. So that's pretty much of our long journey, and we have some few more lessons want to share. And the first one, we can always using incremental updates if we can avoid recompute. If we want to recompute, don't want to recompute from scratch to generate a graph, and but introduce the incremental one also introduce some complexity. So if we build a metadata table for checkpointing, and the state storage is extremely helpful as a developer to debugging, to check the state, to chase the job progress, to recover from failures. And the last one but not least is create for indexing part. If we have deal with some traffic, for example, the read and write traffic, when your server is serving the customers, and you have a lot of batch jobs want to write into Elasticsearch cluster, then if you don't want affect the read performance, you can just write into the new indexing. And once the new indexing complete, you can do a swap. Then it will be transparent to the customer, but you will not lose the performance. Yep, I think that's pretty much of our journey. So we have a few minutes. Would you like to give Q&A sections? Yes? So when I say incremental, is for the graph generation. But as Praveen mentioned, we also have another job called the close connection generation job, which will read from the complete graph and generate the complete indexing. So for all the indexing, it will always keep serving for the current customers. But for new indexing, we also have the complete indexing, including the old indexing, but with some data policy, with some new data, with some freshness data. So once the complete new indexing complete, we will do validation job. If the job complete, we will do a swap. So make sure we don't miss any data.
Yeah. So to answer your question, right? So we definitely has a lot of data. Since we're going to have two indexes having the same amount of data, we definitely store a lot of data in Elasticsearch. But we kind of optimize our Elasticsearch that way that the old index is always optimized for reads, and the new index that we're going to create is only optimized for writes. So that way, the caching evictions can be reduced a lot in Elasticsearch. And once a new index is completely created and it's completely validated and it has all these connections from the orgs, then we change the alias of the Elasticsearch. So that way, it just switches reasonably.
So in the Spark jobs, you mentioned that at some point you introduced your queuing, where each bins you are putting in the queue, and then so what kind of a scheduler do you use in Spark? Like if you use Yarn or something, it has inbuilt queuing capability. So why not to use that?
So we use Yarn as a cluster, and because it's one, as I mentioned, we scale up the Spark cluster, but not the Yarn cluster. Each job, each bucket, and each partition within the bucket, we spin up one Spark cluster. So we use Azkaban as our job scheduler and check this Spark cluster's state. But the job Azkaban can report which Spark cluster failed, but it can't report which job within the Azkaban or within the one Spark cluster failed.
So there are two different factors here. So the first factor is that as soon as there's a new conversation happening with our customers, we immediately get a notification, and then we start to crawl it, try to kind of put into data lake immediately. So the data lake gets updated in a very, very short span of time, in kind of like seconds. And if you're talking about the offline windows or the offline jobs, which has some timing windows, which has probably 1 hour timing windows, so which means that we have almost 1 hour latency for the data to be arrived in the data lake. But in terms of our contact insights, since we have, so these daily jobs runs periodically. So if you guys remember the first example that I showed in Spotify, so there's a Discover Weekly. So it's very, very similar to our stuff as well, the Discover Weekly of the new closest connections. So we don't want to kind of like make a delay of 1 week, but we want to kind of like optimize the computation as quick as we can. So we have these jobs running for every couple of days, and every couple of days, it actually tries to read from the data lake and the existing graph, trying to kind of put them together, trying to show it up to the closest connections.
So, and you were also showing like calls. So are you taking like the voice calls, or are you just taking like what exactly is the input to your this whole graph?
So the voice calls is under progress right now, but currently we're taking the transcripts of the voice calls, which actually helps us trying to kind of do some NLP on top of it, trying to kind of analyze what is the sentiment of the voice call. But at this time, it's mostly about the transcripts. That way, it's still under progress right now. Yes, so there are some kind of immutable conversation that they have. For example, like if it's an email, which is always immutable, which actually helps us trying to kind of keep the data simple and some based on object model. But we have some kind of data, like for example, meetings, where people always trying to change the meetings, trying to kind of add more invitees, trying to change the subjects. So there's always changes to the meetings. So which actually kind of like makes us vulnerable, trying to keep changing the data lake based on the changes of the events. So which is where the metadata store helps us trying to understand exactly various sources all this mutable data is, and using the metadata store, it can help us trying to go to a specific random access of this data in a data lake.
So like, because the question was again, so then the data store you're using, is it like an object store? And if it is, then the updates you're using, how do you all use that random access?
So those object store kind of has some complications. So as long as we have some kind of extra caching layer on top of it, if there's no caching layer, our job is super painful trying to find exactly where the file is, right? So that's where we build our own caching layer, which is very similar to the HDFS caching layer that HDFS has. So this caching layer helps us trying to kind of access that exact point easily. We'll catch up.